Okay, hey everyone, welcome. Welcome to our NAGT webinar. The NAGT webinar series is your one-stop shop for strengthening work in Earth education. Webinars in our series feature novel and innovative work in Earth education, research and pedagogy, new teaching materials, and the classroom and professional experiences of people like you. The NAGT webinar series is free and open to the public, and we encourage you to invite your colleagues to attend and join our discussion. On the screen and linked in the chat is a link to the webinar series where you can find the webinar schedule, an archive of past events, and information on our sponsoring projects and programs. You can find slides, resources, and recordings of each webinar, including today's, through the webinar archives. Before we get started, please take a moment to review the Zoom controls on the screen. We ask that you leave your microphones muted and your cameras off. Live captions are available for this presentation. To turn them on, click the live transcript button in the control bar and select show subtitle from the pop-up menu. If they're showing on your screen and you don't want them, you can do that same thing and click hide subtitles, and that will turn them off for you. If you have questions and comments along the way, we encourage you to enter those into the chat box. Webinar presenters and staff will be monitoring the chat throughout the presentation. A reminder that participants in all NAGT meetings and events are expected to abide by the NAGT Code of Conduct, which applies in all venues, events, and online forums associated with NAGT. Please read the full NAGT Code of Conduct policy linked in the chat for details. Today's webinar is titled The City as the Field, Inclusive Early Undergraduate Geophysics Teaching Modules to Address Urban Environmental Challenges, presented by Andy Parsekian from the University of Wyoming, Sarah Cruz from the University of South Florida, and Elise Slater from Rutgers University in Newark. Thank you all so much for participating in our webinar series. You can go ahead and take it away.
Great, thanks a lot for the introduction, Bradley. So we're going to get started here talking about in the city and field, inclusive early undergraduate geophysics teaching modules to address urban and environmental challenges. So the project title that we have is called IGUaNA. So this acronym is going to be throughout the presentation, and it stands for Introducing Geophysics for Urban and Near Surface Applications. And IGUaNA is affiliated with IRIS, which is the Incorporated Research Institute for Seismology. So we'll just pile on the acronyms here. And it's an education and public outreach project within IRIS. And the mission mainly is to develop inclusive geophysics-related coursework aimed at engaging students from underrepresented groups with a particular focus on urban environmental problems. So we really have the mission, the goal of increasing participation of students from historically marginalized groups in geoscience broadly, but we do have a focus in geophysics thanks to our own research expertise and the mission of IRIS in general. So the university collaborators in this project that Bradley just mentioned are Rutgers, Newark, where Elise Slater is, and University of South Florida, where Sarah Cruz is, and I'm at the University of Wyoming. Of course, we also collaborate with the Science Education and Research Center at Carleton College, and Carol Ormond is our primary collaborator there, who will not be speaking today, but she's in the room, hopefully to correct any major missteps if we make them. So the overarching goals that we have are our sort of driving mission is to attract a diverse population of students to geophysics. We want to do this through developing curricular materials that highlight the application of geophysical tools and geophysical methods to a range of environmental engineering and geoscience problems. One of our major goals is throughout all of these parts of the module that we're focusing on societally relevant problems to develop better connections and meaningful connections with the students in the classroom to hopefully encourage them to continue with geophysics in some level throughout their studies. And finally, we want to make sure that all of the course materials, the curricular materials, include relevance to environmental problems in urban settings to some degree. So one of the major things that we need to achieve with the course materials is to be inclusive. And what does it mean to be inclusive coursework? Maybe you can imagine what it would mean to be inclusive with a group of your friends and a new person comes, but what does it mean to be inclusive in terms of coursework? So we define this as highlighting the appeal of geoscience majors through these societally relevant themes. So you're going to feel more included if you can understand why this application has a relationship to society, maybe your local community, but also more broadly societally overall. So inclusive coursework should have an engaging structure and format that is appropriate for a variety of skill levels. So it should be designed so that it can address one of the major issues with teaching in a classroom, which is that some students are going to be a little bit farther behind and some students are going to be a little bit ahead. And so we try to design it to address the issue of different skill levels in the same classroom, and indeed of different skill levels of classrooms overall. Related to this is that inclusive coursework should include varied, early, and frequent assessment that enables dynamic revision. And so this is, again, to address the issue of different skill levels in the same classroom by being able to assess the students frequently with different measures. You're more likely to be able to make small changes throughout the course of a class meeting or a week or a unit in order to make sure that as many students as possible are following along. And finally, inclusive coursework should show how practitioners, so in this case, geoscience or geophysics practitioners from a range of backgrounds, have a place of the discipline. So we understand that students are going to feel that they have higher probability of actually finding a career in geophysics if they see people like them included in that discipline. So why is this so important? Well, there's not really, what's the point of trying to engage a broader segment of the population if we're unwilling to consider the perspectives, needs, and motivations of the students? And so some examples here. So first of all, a lot of geoscience obviously is related to topics that may be appealing to field-oriented people or, those who have outdoorsy themes. And if there may be a perception, right or wrong, that if you don't fit into that category, then you're not welcome or you're not included. And so that's obviously not true. Anybody who's been in geoscience for more than a few minutes knows that there's a whole range of field and lab and numerical computational stuff that can include everybody. And so we want to highlight that opportunity. Another reason that's important is because when we're trying to see a more diverse geoscience workforce in the future, we recognize that there's a lot of potential students in urban areas. Urban areas are naturally densely populated with people. However, they may also lack access to natural areas just because of their geographic location. So giving examples that show how geoscience can be used even in urban areas or near urban areas is important to highlighting inclusion. And finally, this is an opportunity to leverage research-based pedagogy, right? So not to try to use pedagogy that has been demonstrated through research processes to engage that broad range of learning styles and include everybody who might learn verbally or tactically or through writing, whatever it might be. So the next question that to sort of explain here is why we focus on curriculum. Obviously, there's many different ways that we can approach the issue of diversity in geoscience. And so why have we chosen to do this through curriculum? Well, achieving this diversity, equity, inclusion obviously requires overall systematic change in our educational system. So we need to look at that educational system as a system and leverage approaches wherever we identify these exclusionary inequities. And so as educators, curriculum materials are a component of the system. Curriculum materials have the ability to fit into this attract, support, prepare framework. So the themes addressed throughout a curriculum can attract or repel students, depending on if it's done well or done poorly. They can support students and remove barriers, or if it's designed in a way that's not inclusive, it could present barriers. And finally, curriculum materials could prepare students for the next stage. We can show students what the next step would be in order to continue in this academic field or potentially in a career. Or if designed poorly, the curriculum materials could turn students away, which of course we don't want to do. So what are the barriers that we consider when developing the IGUaNA course materials? Well, one of them is that we recognize that there are many students who just didn't get much exposure or have misconceptions about the geoscientists. So for example, coming in as college first-year students may have had simply limited exposure in the past, may have not had an opportunity to take any kind of geoscience course in the past, so they just don't know about it. Or they may have had no coursework at all in any geoscience theme simply because the curriculum that they had to follow in high school just didn't have room for it. There are other barriers like cultural barriers. So for example, a student's family members may perceive that professional training, like a law degree or an engineering degree or medical degree, is preferred because of their own family values. And there's nothing wrong with that, but it also is fair to say that there's nothing wrong with the career in geoscience just because it's not one of these sort of professional training degrees. And finally, there are some aspects of the geoscience career that may be really attractive to privileged students. We might, those of us who have the most privilege may be the ones that are able to go outside into natural areas and be inspired by geoscience from that perspective. But those same aspects may be completely undesirable to students from historically marginalized groups. However, if we can help everyone recognize that this is, it's not necessarily required that you do some of these things, like do field work if you don't want to, then it can still lead to a fruitful career. So who's the target audience for the course materials that we're talking about today? So it is primarily early stage undergraduates. The objective is to expose first and second year undergraduate college students to geophysics and geoscience principles so that they may have the opportunity to get interested and take further coursework later on. So it's not too late to pitch geoscience as accessible for anyone. However, this could be realistically, these materials, we would be thrilled if anybody used them. So while we're really hoping that folks who are teaching on urban campuses or maybe two-year colleges, or maybe you're just at a regular four-year research university, but you teach a first-year course, that's ideal. That's our ideal demographic. However, anybody who uses this, we're thrilled with. There's potential this could be useful in more advanced high school classrooms. So for example. So one of our themes throughout IGUaNA is that we aim to have adaptable course material. And what we mean by that is it's adaptable. It's as adaptable as possible for instructors to get into their classrooms. So we want there to be as few barriers for the students, but we also want there to be few barriers for those of you who might implement these course materials in your classroom. So we design them in a modular format that allows you to pick and choose what you need when you need it, but we also provide pathways and ideas for how it might be able to fit into your courses. Everything is designed to be easily available and essentially complete, so plug and play if you're not already an expert geophysicist. We facilitate access to the resources, data sets, and instrumentation, and we assist faculty with the objective of assisting faculty who have limited time to develop their own new course materials. So on the right side, this is a graphic of some different ideas for how these course materials may be embedded into your courses. If you wanted, you could just run all of our course material together. It would take about 6 or 7 weeks and about maybe half of the semester, and you could call it a half a semester course if you wanted. You could choose one of the modules, and we'll be introducing those momentarily here, and embed that as a complete part of a course, right? So you take 3 weeks or whatever, 2 or 3 weeks to do that module, and then continue on with the rest of your course. And then finally, it's totally reasonable that you might like a PowerPoint that we designed, or you might like one of our assessment tools, or you might want to use one of our exercises, and you completely ignore the rest of the curricular design, but you use some of the components, and that's obviously fantastic as well. So we do try and do some place-based problems in the class, and two of the examples, and Sarah will talk about a third momentarily, are an urban wetland in New Jersey and an urban renewal project in York, Pennsylvania. And we chose to do place-based learning approaches in some cases because we're trying to connect with real data sets. We're trying to use real data to show the students, this is not just something that we made up. This is a real problem. This is real data. This is some way somebody solved that problem. And so that's just, again, trying to be more inclusive and connect with the students. But before we jump into introduction of the modules, I just wanted to see if we could have a really quick text-based chat discussion. So just using the Zoom chat tool to think about these questions. And these questions, I believe both of them are pretty much verbatim from Stephanie Sitt, who is at the University of Illinois, Chicago. She does education, geoscience education research. I just thought they were really terrific questions. So the first question is, what are some places that you have a strong connection with, and how do they inform your knowledge about geoscience? But then the second question I think is really informative is, how do the places that you have a strong connection with differ from those of your students? So while we switch over to Sarah, if everyone who has that chat box want to put up some ideas, we would be super interested to hear about your thoughts about places that inspire you related to geoscience and how those might be different or similar to what your students experience.
So thanks, Andy. And I'm Sarah Cruz at University of South Florida, and I'm going to give a brief overview of the ground penetrating radar module, just some highlights, and then hopefully save a few minutes of time for you to try one of the apps that comes with this module. So I'm just going to walk you through some selected slides from the module, and I have lost my PowerPoint advancing capability. Sorry, just a moment. Right, I'm going to unshare my screen and try to recover my PowerPoint. And share this. Okay, so we start with something that the students might already be familiar with, which is some medical imaging techniques, and ask them to watch some videos of this, and then compare it to a video of how ground penetrating radar works. So you get the idea of remote sensing. We emphasize in the first unit, it's divided into 3 units, apologies. We also emphasize in this first unit that ground penetrating radar images are a distorted view of the subsurface, that in order to interpret real ground penetrating radar images, you need to know some geophysics and have some understanding. It's not the magic ground penetrating radar of Hollywood. In the second unit, we get a little nittier grittier, how you actually calculate the depth to an object that you can see in a ground penetrating radar image, how you get the velocity of the radar wave to compute its depth. And the practice app that we'll have a couple minutes for at the end of this is actually let you do that. To give students an idea of why you get a distorted version of the subsurface, we have some videos that show what happens when a ground penetrating radar transmits an electromagnetic wave. So the top figure is showing GPR waves traveling through the ground and back up to the instrument. And the bottom is what the user would see on the screen as you're acquiring data. And you can see in this hypothetical example up here of a simple buried pipe, the ground penetrating radar signal of that simple buried pipe is this upside down U, or it's a diffraction hyperbola. And this is going to be really important because we use the arrival time of the apex of the hyperbola and the shape of the hyperbola wings to calculate how deep the buried object is and what the velocity of the radar wave is. So your exercise is to go from this image to figure out where was this pipe actually. In the third unit, we describe some of the limitations of just working with a single ground penetrating radar profile, how you could, in this example, we'll show a case study where tree roots were mistaken for graves, and why in some places you need to collect a lot of profiles. So in this third unit, we talk about how practitioners will collect multiple parallel or other GPR profiles, and put them together to make a map of where in the subsurface we are getting a lot of reflected energy back. And this will help us look at the map view of the buried objects that are producing the returns and distinguish things like tree roots from graves. And this is just another example slide where we show students that if you just do a single one single 2D profile, a grave could look very much like a tree root. And then the case study in the third is actually based on horrific work at a reform school in the panhandle of Florida. It's actually the true story that Colson Whitehead based his recent novel on, if you've heard of this novel, Nickel Boys. And GPR has a little role to play in the story of this. So ground penetrating radar surveys were used to detect the graves of boys who had literally died at this reform school. And a second survey was later run when they suspected that there might be more graves, and 27 more graves were reported. But when they dug here, they discovered that those reported graves, in fact, were just tree roots. So students in this third exercise are led to understand how this could happen and how you need to be careful in interpreting data. We also give you information on how you can find out how likely GPR is to work in your soil type in, at least in the United States. We have the information there. And now I just want to lead you to this app. I put a link to the app in the chat window. And this is just one of the apps available. And can you see the app? Are you seeing a blue and yellow image on your screens? Okay, thanks. So this app contains 4 GPR data sets over different targets: graves, tree roots, utilities, volcanic blocks. And for each data set, we open it with an introduction about where the data were collected. You can hide these location details and go straight to the GPR profile. And then beneath the GPR profile, there's 3 slider bars. And the slider bars control the shape of a hypothetical diffraction hyperbola. You can set the X position along the profile, and then you can set the arrival time of the apex of the hyperbola. And the goal is to match the hyperbola to one of the hyperbolas that you see actually in the data itself. The third slider bar, you're setting the velocity of the radar wave in the ground, which determines the shape of the hyperbola. So the goal is to, when you have a good fit to one of these, then you have the travel time of the GPR wave down and back up, and you have the velocity, so the students can take these 2 numbers and calculate the depth to the buried object. This is a series of graves of an African-American burial ground that actually happens to lie underground on high school property in Tampa, Florida today. So now Bradley will let us know how many minutes are left for you to actually play with this app. So go to the chat window. Maybe I will make sure that it's in a prominent location there. And yeah, there it is at the bottom. Thanks, Carol. If you click on that, you should be able to access this app yourself. So take a couple minutes, play with it, see what GPR profiles from these different settings can look like. And there'll be time for some Q&A afterwards, so I'm happy to answer questions later. No, you're absolutely right. I see a comment. Yes, perhaps a trigger warning would be appropriate, a content warning. On the other hand, the content is engaging in a way. It draws you in. It's important. Oh, I see a suggestion to not start with a Graves data set. That's a great idea. Put it at the bottom behind the much more commonplace tree roots and buried utility pipes. Absolutely great idea. Thank you.
Okay, Andy, I think you want me to start.
Can smoothly transition into the next unit, I think.
Okay, you're ready for me? I wasn't sure if you were ready for me. Yes, absolutely. I'm going to post a link into the chat box here as well, which will be relevant to the resistivity module I'm going to talk about here. So this module is focused on the electrical resistivity geophysical technique, and it attempts to use real data from a field site that's local to Rutgers Newark, which is located in Newark, New Jersey. And this field site is between Newark and New York City. And it attempts to connect students to the world around them. And it's designed, as Andy said, to be flexible. So Andy emphasized the flexibility of these modules, and that's certainly the case here. I'm going to take you briefly through the different units, but I should have mentioned straight away that there are ways to streamline these and cherry pick, and also merge the more introductory material at the beginning with the more summative integrated material at the end, depending on the level that you're targeting. So the flexibility is important here. And this is just a photograph of the site, which is a wetland in New Jersey that's in an area of New Jersey which has been heavily environmentally degraded by industrial activities in this area of the country, but it's actually gone through a remarkable restoration. And so you see the natural wetland there. The next slide, Andy. So the first unit really introduces you to the site, and in fact there isn't really any geophysics in this first module. What this module does is really sets out a hypothesis for a particular element of this restoration of this wetland, and that is what's controlling the spatial distribution of native plant species that are recovering and re-emerging in this wetland. And the red in the figure here is a certain plant, Salicornia, commonly known as a pickleweed. And the whole module really focuses on, can we use geophysical data to explore a hypothesis? And the hypothesis that we put forward is that it's variations in salinity that are controlling the distribution of this vegetation. And so the students really use the geophysical data to explore this hypothesis. And there's two key parts of the unit one. One is the story map that I posted the link to, and that really ends up being a part of the modules that students use as they progress through the set of modules. And also there's a video, a flyover drone-based video that really provides an introduction and talks about the field site and sets the scene for the use of the geophysics in this field-based study. Next slide, Andy. The second unit really dives into the basics of electrical geophysics, and it really focuses on what is it that controls the electrical conductivity that we measure with this technique of soils. And it's a simplified version of the true story, but it focuses on salinity. It focuses on the ionic concentration of the fluids in the ground controls the resistivity. And so the idea is that we can use geophysics to map spatial variations in salinity in this wetland. So salinity of the subsurface water in the soils. And this unit takes a dive into the basics of geophysics, but it also uses a case study on another wetland in the same area that was studied extensively to examine the impacts of landfill leachates on the wetlands in this area, where students explore how these methods have also been used to map out contaminant plumes coming off landfills into these degraded wetlands. Next slide, Annie. And so Unit 3 then really focuses on how do you collect geophysical data. So it focuses very much on what controls the measurements that we acquire with the geophysics. So the idea is that the students explore some basic parameters that decide that a geophysicist has to decide on before they collect a survey, and what impact does that have on the data they collect. So there's some exercises here that explore those concepts. What frequency do we use? If it's an electromagnetic sensor, what is the spacing of the coils? And then there is a module, an Excel-based exercise that if I have time, I'll briefly show, that simulates electrical resistivity data sets and shows how choices about how you set up an electrical resistivity survey impact what you would be able to image with the geophysical method. Next slide, Andy. The fourth unit dives into the mechanics of what's called inversion. And this is what geophysicists use to convert measurements into images of the subsurface Earth. And so this can be quite a complicated subject, and maybe this will be for the more advanced students. But this unit specifically takes the students through how does this magic of geophysical inversion occur. And it uses an open source piece of software that was recently developed by a group of students, actually, and it's called ResAPI. And this is a Python-based visual graphical user interface that is very user-friendly and does a great job of simplifying the mechanics of this concept of inversion, which in inversion is a critical part of geophysical data sets. The next slide, Andy. And then the Unit 5 really brings it all back together. And this is where, if you're a bit wary of the Units 2 to 3 because of the detail, you can actually almost merge Unit 1 and Unit 5. And Unit 5 gives you the geophysical data sets that were produced in Units 2 and 3 and 4, and allows you then to explore this hypothesis that I mentioned in the first unit, which is how is the geophysics informing on whether it really is variations in salinity in the subsurface that is controlling the distribution of these vegetation patterns. So this is very visual, and if you play around with the story map I provided the link to, you can zoom through it towards the end, where you'll see some interactive tools which include sliders that allow you to overlay the geophysical data sets that were required, which are measurements of conductivity, and conductivity should be approximately proportional to salinity of the fluids or the soils. And the students are able to investigate that patterning and explore, well, does the hypothesis generated at the beginning correlate with what we find in the data? Is the hypothesis supported by the data set or not? And this unit has concepts of hypothesis testing involved in it, and asking the students to evaluate what do the geophysics tell us about this hypothesis, and what do they think of the interpretation of the geophysical data set. And I think that's the end of my slides. I'm not sure how much time I have left, Andy. I meant to put a timer on, but I didn't.
You should go for it. Take 3 or 4 minutes.
3 or 4 minutes. So you can, let me just share my screen. If you're not there yet, you can go to this storybook. And so you should see the storybook now. And as I said, this really takes you through the whole story of the case study. And it begins with some looking at the field site, and the vegetation patterning is the key thing here. So some high resolution images of these vegetation patterns. There's some introductions to the plant itself. And then as you move further through the storybook, it starts describing how the data were collected and shows the location of the data. And this includes a line, which is the electrical resistivity line, and then these yellow dots are measurements made with a frequency domain sensor, which is a more rapid way of measuring spatial variability and conductivity. And then as you move further through the unit, it then gets to these interactive tools where the students can explore to what degree does the vegetation, the patterning, compare with the conductivity patterns observed with the geophysics at different depths. So these conductivities are measured at different depths. And so they get a bunch of layers that they can use this slider tool to explore that correlation. And then lastly, if I, in a few, just a minute I have left, the Excel tool I mentioned is a very nice tool for just getting a sense of what can you really expect geophysical data to provide. They're a very, geophysics is a very, it's not a robust way of looking at the subsurface. It's very flawed. So students get to explore, okay, if I've got a real subsurface that looks like this, like a bunch of blocks, if I set the survey up a certain way using the geophysical survey design that I can choose a few different things, a different survey geometry, I can simulate different data sets. And there's a couple of preloaded different studies here. So there's this blocks one, there's an underground storage tank, and then there's some things that simulate contaminants in the subsurface. This is supposed to be an oil plume, and they can simulate what you would see based on different geometries of the measurement setup. And with that, I'll finish, Andy.
Great, thanks, Lee. So the third geophysical method that we cover in IGUaNA is seismic refraction imaging. And the motivation with this unit is that the physics are comparatively straightforward in that they can be basically explored in detail with pen and paper, or in our case, we primarily focus on Excel-based exercises. And so this is intended to be more engaging because the students, or as engaging as possible, because the students can see the equations and work the equations themselves and get a full understanding for some physics that are very real in terms of what happens in the field. The second motivation is that is the objective to engage students through relation to everyday infrastructure projects. The great thing about infrastructure is that everybody's encountered it, and often there are elements where you need to have some information about the subsurface in order to plan and design those infrastructure projects, and that's where the geophysics comes in. And so seismic refraction, because it is based in these really straightforward physical equations, we view as a springboard to other more complicated geophysical methods. So again, relating geoscience to infrastructure, this is kind of leveraging this opportunity that we have in the built environment, because the built environment is this geoscience engineering nexus. I mean, here's three really straightforward examples that anybody could basically imagine, or maybe even look outside their window and see, right? So if you want to build a building, you're going to have to plan for excavation. In some cases, geophysics may give you information. Seismic refraction in particular may give you information about planning that excavation. Remediating sites, back to the contamination idea, if you know how thick your overburden is, then you may be able to predict where contaminants would flow. And similarly, if you want to bore for a subway tunnel, you need to know, how durable that rock is and how difficult it's going to be to bore through. And again, there's an opportunity for geophysics. So with the seismic refraction unit, we have seismic refraction module, excuse me. There are three units, and the first one is basically the introduction to shallow seismology, basically how geophysics can be applied to various problems. And we start with a very brief introduction of the speed of sound in the earth, right? Seismic refraction is controlled by the speed of sound in the earth. In the second unit, we talk more about how seismic waves travel through the ground, and also this idea of conceptual models of the subsurface. So it's sort of like the idea that we have in our head of what might be underground. To geoscientists, to all of us, this is a very straightforward idea, but to students who haven't thought about developing those conceptual models, even if they're simple, layered, like soil over bedrock, we kind of lead through how to think those things through and how they are useful for thinking about how seismic refraction might give you information about the subsurface. And then finally, we talk in Unit 3 about this case study in Coder's Creek, which is in York, Pennsylvania, where the city decided to do a urban renewal project around what had been a very contaminated waterway. And in order to do that renewal project, they needed to plan for some excavation. And so a consultant did a bunch of seismic surveys, and they were kind enough to share those data with us. And so we've incorporated those real data that were used for a real urban renewal project into the coursework. And so the students can actually analyze those data themselves. So the types of things that you encounter in this module include talking about the physical equations in a really clear and diagrammed way, and thinking about why different parameters lead to different outcomes. There are some simulations, animations helping to illustrate some of these ideas of waves that are transmitted and refracted. And then there's, of course, the components of the case study, which include real data and Excel workbooks that help students work through that real data. And so I think that's one of the highlights here, is that there's some expectation that the instructor is willing to work with students to understand Excel, because we provide the exercises with these Excel-based spreadsheets. But that's a very powerful opportunity, because what I find as an instructor of undergraduates is that at the end of their undergrad degree, they're like, I really value being able to use Excel in my future job or whatever it is. So this is a jump start to say, hey, look, not only are you learning about geophysics, but you're learning a really tangible, transferable skill that you could use for a lot of different things. So I wanted to give you guys a quick example of one of the workbooks. And so in the chat box right now, I'm going to paste a link to everybody. And we'll talk about access to the materials momentarily. So if you go to this worksheet, and then you will find something that looks like this. So we provide it in an XLS, downloadable workbook, but it also works in Google Sheets if there's an issue. And URL doesn't exist. That's interesting. Well,
Your link's
you may have
not
to follow along. Did I not copy the whole thing? Maybe that's the
You
problem.
didn't copy the whole thing.
Oh, indeed, you are so correct. My apologies. Thank you for that. Try that one. Everybody is joining me. Look at all those Google animals at the top popping up. Great, I'm glad it worked. So basically the idea is here we have a seismic refraction data set. So on the left side top is where the shot was, and that sent energy across the image from the left towards the right. And the data that you're looking at is that my mouse is going across is that direct wave, where the energy is going directly from the transmitter to the receiver across the ground surface. And then the refracted wave in maybe 1 or 2 refractions is shown as the slopes that are getting more gradual. And so the idea with this is that students can look at this seismogram, and they can pick out the travel time. So let's see, I'm going to cheat and look at the solution so I don't have to pick it off the image there, because my eyes can't see it right now. But it's something like 0.3. Oops, that's going to be 0 and 0.3. And they can find that the 30 is going to be 0.85. And so based on these travel times, you can then calculate the velocities, and then the velocity will get incorporated into this final equation. So the students have to be able to or be willing to try to put these equations in. But there's a lot of flexibility, because I provide the solution. So if an instructor wants to provide the solution to the students so they can just play with the solved version, then they can do that, right? All the equations are visible, typed in, so you can work backwards that way. The other feature is, let me just find, is the worked example. So if you're quick before anyone else comments, you should be able to go to this worked example. And so if students are struggling with the Excel elements, worked examples are provided for all of the exercises, where you can go through and actually sort of each individual step that you need to do, everything that you need to put in the Excel sheet, and all the equations as well. So try and make it as accessible as possible, even for students who are just experiencing Excel for perhaps their first time. So you are all welcome to continue playing around with that. In the interest of time, I apologize for racing ahead a little bit here, but I want to get to some of these important questions or these important wrap-up comments here. So We provide all of these units with context from real data sets collected in the field. However, we also provide each of these units with some kind of instructions on how you might collect your own data set in your own classroom. How do you do that if you don't have a $30,000 seismic instrument? No problem, we can get it for you. So currently, while this IRIS EPO project is ongoing, we have the ability to loan equipment to you at no cost, free for HBCUs and MSIs, possible subsidies for all requesters if you contact any of the workshop organizers. So that would be Sarah Lee, Carol, or myself. We can help you get that. With the Iris Pascal Instrumentation Center in Socorro, New Mexico, owns the seismic equipment and the radar equipment, and they can mail it right to you for use as, in your classroom, collect your own data. And the University of Wyoming can do similar with electrical resistivity equipment. So if you have the time, it is possible to get hands-on with this. If you don't have the time or you don't have some other resource, then of course all the authentic data is provided through the course modules. Then the most important question, when is the stuff available? So where are we right now? External pilot testing is complete. We are finalizing some internal pilot testing right now, just making sure everything works as we think it should. Completing the final revisions this fall, hopefully within the next couple of weeks. And so that means it should be published to the public, free access for anybody, basically in the winter. So December, January timeframe. But for you, because you are here today, it is available to you. And if you want access after today, Carol, if you contact Carol, she can allow you access to the course materials through the CERC website. And I think Bradley is going to administer another poll. What we are most interested in is things about how you might be able to use these course materials, what kind of courses you might use them in, and how likely you would be to include the field component if you were to use some of the course materials. So with that, we wanted to leave a few minutes for discussion and questions. Sarah and Lee, if there's any closing comments you wanted to make, I would invite you to do so. Otherwise, we can open it up. I don't know if it's safe to do just speak up or raise a hand, or maybe Bradley can provide some guidance on that. Thank you so much for your time to come and hear about IGUaNA, and thanks for your participation in our 2 engagement exercises.
Yeah, thank you. Thanks, Andy and Sarah and Lee. If you guys all have questions, you guys can unmute, turn on your cameras and ask questions, or you can put them in the chat. We can answer them there. So whatever works best for you. There's a question from Alan asking, do you have insights from your work with students about whether urban focus was effective at fostering engagement?
Carol, do you think that came across in some of the responses from the pilot surveys?
Yeah, thanks for asking. I was just starting to type into the chat, but that's a very inefficient way to answer it. Yes, the short answer is yes, but also in addition to the fairly high level of engagement for the students, they felt that the materials helped strengthen their skills, and we asked them about a wide variety of skills, quantitative skills, data analysis skills, problem solving, that sort of thing. Yeah, so the materials, the responses we've gotten from student surveys are really very encouraging.
So I saw a couple of people mentioned about gravity. It's like it seems worthwhile just to mention generally. So what is the next step? What is the future here? So the immediate future is a synthesis module that hopefully will be available maybe in 6 to 8 months, which will integrate the GPR, the resistivity, and the seismic. So that's our first priority. We're kind of committed to working on that. In terms of other methods, I think this is a huge opportunity. As time goes on, people could tackle elements of other methods if they have the resources to do so. I think one way is maybe if somebody's working on an NSF project, they can include a broader impacts element that includes developing one of these IGUaNA modules. That would be amazing. I think the authors that are here in the room would like to work on that stuff. It's going to depend on time and resources. It would be great to know what would be popular. And so it's good to hear that feedback that gravity would be interesting. So we don't have an immediate plan to include gravity, but it's a great idea. And I hope someone is willing to work on it.
I see a question about what kind of classes they were tested in. One of the tests was an intro chemistry class, which used units 1 and 5 of Lee's resistivity, which is really, you know, sort of a urban wetland environmental problem, so appropriate for that. They were tested in intro geology, classes that draw non-majors as well as majors. And it seemed like, you know, that it was, students felt like it was fairly compelling material to engage with. I taught it without doing actual field work because I used these in a pilot test during COVID. And again, I think students were reasonably engaged, you know, even though they didn't get out. Now, we have done a pilot test where, you know, they shipped the ground penetrating radar from IRIS to Fort Valley State University. And I think they really enjoyed that. The risk always with that is you don't know exactly what you'll see, but we have backup data in case you don't see anything. So we do try to make a good facsimile of if you could collect this data yourself. I don't think, I mean, Carol, do you have a sense? I don't know if we have any comparison points yet for collecting it yourself versus.
Yeah, I don't think we have enough data to answer that question since it's really only the Fort Valley folks who collected their own data at this point. It's a very, yeah, it would be a small comparison group.
I will say about what levels were the modules tested. So the modules were tested at intro levels, but the resistivity module, the units 2, 3, and 4 go well into what you might actually include in a geophysics class. So they all start at the very beginning, but they go to different levels. And we try to make them varied. Like the GPR module does not use Excel while the seismic one does. So you have multiple options.
And Lee wants to respond to this question from Katie. Lee, do you want to just jump in on that?
Yeah, I just wanted to, well, actually, I just wanted to say I like the idea. And I mean, obviously, it's something we'd have to talk about as a group, but thought it was a pretty interesting concept and kind of gets at the idea that we had at the next step of this is to actually do something that incorporates real data more, that one might collect. That's one element. The other element we've been looking at is some kind of integrative module that we would put together at a place, the three of us. But this is a different kind of thing to consider, I guess. And I think going forward, we should discuss this.
Yeah, I like the idea of crowdsourcing that. That's, you know, a way to cast a really wide net. So I like that a lot.
I think, you know, one of the things that I would do is maybe provide data that would be more geographically relevant to different institutions. I mean, obviously, the data sets that we're providing are geographically relevant to our own institutions, or at least mine is, and yours is, Andy. Well, no, yours isn't. Yours is not geographically relevant to your institution. But if we actually had the opportunity to bring in data sets that we could build around, then you could maybe have more data sets that would resonate with a wider range of students, perhaps.
Are there any last minute questions? We have about 5 minutes left. In the meantime, I'm going to post the evaluation survey for this webinar. It helps us out a lot if you guys take the time, just a couple minutes to fill this out and give us some feedback on how this webinar went. So please take a minute to do that. And thank you again, Andy and Lee and Sarah. This has been a great presentation. Lots of really awesome resources that I think a lot of people are looking forward to later this year. So thank you guys again.
Thanks, Bradley. Thanks, everyone.
Thank you.
Thank you. And we look forward to hearing from you if you use them. Would be great. And at least this next year, while we're still working on the grant, we can help you too. Thank you.
That's right.